All right, we're going to move into the next subject, which is the notion of countability. And I'm going to start with this very simple idea that if we have a point in a set, that point will be contained in some open sets. And I'd like to we'll just use this sort of plane and the open ball, but understand this is an abstract idea, right? The open ball is representative of an open set, which is an element of the topology of this space, whatever space we're talking about, and the point is an element of the underlying set. So if I call the point, say, P, P is an element of the underlying set X, and this is a topological space. So it's a set X with a topology. So P is going to be contained in some open set. But an open set is a union of other open sets. So the question is there another open set contained in the first one that has P in it? And then you ask the same question again, and what you end up finding is that you'll have this nested collection of open sets that contain the point P. Now that nested collection could terminate, and you can almost imagine in some of the examples we gave last time that it might just be 1, 2, 3 and then stop. There's no others. We'll show some examples of that. But of course, generally speaking, certainly in this open ball topology, there's an infinite number of these nested open sets, and they just go down forever. And as long as you don't have the discrete topology, there will always be more than one point in the set. If you have the discrete topology, then P itself is open, right? So that makes things a bit messier. But assuming you don't have the discrete topology, you're somewhat weaker than the discrete topology, there's going to be very often an infinite number of these open sets. The question is not whether there's an infinite number of them. The question is there a countable number of them? And for example, in the open ball topology, clearly there's not a countable number of these. There's an uncountable number because every diameter of these open sets in this open ball could be just some element of the real numbers. So if the diameter of each open set comes from the real numbers, this is certainly going to be uncountable. But that's not really the problem, because you could always create a countable bunch, right? We can just say, oh, we're not going to, although we could draw from the real numbers, we're not going to. We're going to draw from the rational numbers. And once you do that, now all of a sudden you have a countable number of open sets that nest together around an element of the underlying space, which is X. And if you can do this for every point, if for every point you can create a countable, I'm going to stop dotting the lines, a countable sort of nested collection of open sets, we're really dealing with something in the literature it's called open neighborhoods, right? These are open neighborhoods and they're nested open neighborhoods. If you can if you can pick out a countable number of these, even if it's infinite, if it's countable, and you can do this at every point in the space, then your space is called first countable. First countable. So first countability is about the properties of a space at every point. And every point you can create what we call a countable basis at each point. So this would be a countable basis at each point. And because of this, this space, the plane, for example, is first countable. Now, the notion of being second countable is a little bit different. To be second countable, it's actually a little easier to understand. Any open set, right? So if we're dealing with the plane here, right? This is an open set on the plane. Any shape, right, that we can make with our basis, right? Which in this case was balls. Now everything's open here, right? So I'm just not dotting these, right? So any open set can be constructed by elements of its basis. So the basis of the topology with these open balls certainly we can do this and we can build any shape. Now the question is can we do this with a countable number of open balls? Can we is every open set in the topology, is every open set the union of a countable number of members of the basis? So can I find a basis where I can build any open set from a countable number? And that could be any open set in any location, anywhere in the plane, of any shape or size, any open set. The question is, can I build it out of a countable number of basis elements? And it turns out in the real plane, using this open ball topology, I can. I can, just by restricting to rational numbers, I can still count all of the open balls that are building this shape, but I don't have to use real numbered diameters or real numbered positions of these balls. So this space would be second countable. So second countable is a property about any open set, and first countable is a property about any point. So second countability, if you're second countable, you're definitely first countable, right? But if you're first countable, you're not definitely second countable. So this countability requirement is important for manifolds because all of our manifolds have to be second countable. And ultimately, the reason that we demand second countability is because there are many topological properties that are important that second countability will guarantee, and it has to do with stitching together manifolds and having manifolds that behave well. First countable and second countability are pretty important. And we can look at a few examples from our bunch of lines, right? In our basic open interval with the Euclidean topology, right? Well, certainly every point will have a potentially countable open basis. So it's definitely, the Euclidean topology is definitely first countable. And certainly any open set, any one of these open sets can be built up of a finite, not a finite, but a countable number of other open intervals. So it's first countable and it's also second countable. What was this? The nested interval topology. Remember this thing that has intervals at 1/3, 2/3, 3/4, etc., right? This point here is in an open set. It's in this open set here, and it's also in this one, and this one, and this one, and it's completely countable, right? So this is also second countable and first countable, the nested interval topology, nested interval, because every point, right, that point, it's contained in an open set, and that open set's contained in another one and contained in another one. Now this is an example where this point you can't get, there's not an infinite string of them. Well, there is an infinite string of them, but it's not nested forever, right? Because it's not very separable. This is an example of where the separability issue is kind of interesting. But nevertheless, it is first countable and second countable. Then we had, I think, we had, what was the other topology we had? Well, we had this closed interval topology, right? Like this, where we had an A and a B like that. And this included all of these half-open intervals like this and all of the open intervals that contained 0. So for this object, right, we can also take, say, this point, and we can, and there it becomes very similar to the nested interval topology, except that B could be real, right? So because B is allowed to be a real number, there's actually now an infinite number of these. But that's okay, because all we do is select a countable bunch. And we're able to create a countable nested set of neighborhoods that captures that point. We could do that for this point, and we could do that for that point. So this is also a space that is first countable and second countable. Now we go to, say, the cofinite topology, right? Remember the cofinite topology? where we omitted points, right? Say we omitted 2 points, and then we created these open intervals, and the open set is the whole line sort of missing those points, or the whole interval missing those points. Well, now, actually, say we were interested in this point right here. Well, there we certainly made a topology that we found an open set that contains it. That's not a problem. But can we find a nested open set that also contains it? Well, any other open set would necessarily have to be different, which means that it would have to exclude different points. So if we excluded, say, that point, then all of a sudden we have the new, I better do that in red. Say we omitted this point, right? Well, this new open set definitely contains our point. Well, that's good. But you'll notice it is not nested because it doesn't contain these 2 points, which was the other one, which was from the other open set that contained our point. And in fact, this is pathological. We cannot ever create a nested series of open sets. So this is not first countable. This is not first countable. Likewise, this set is also not second countable because we can't invent a finite basis that can build every single open set. So this is neither first countable nor second countable. So this is this is where spaces become like dysfunctional and odd, and that's exactly what we want to avoid when we build manifolds. In the last lecture, I also talked about another topology of these line. It was called the lower limit topology, right? And this was the topology where the basis sets were taken to be open intervals like this, where B and A are real numbers. So this would be not an open interval, a half open interval, but it's considered to be a member of the basis. So this becomes an element of the topology, lower limit topology, I think is what we should call it. And this is a topology because these things are in the basis. They're all the intervals, so it's very similar to the Euclidean topology, but we just now are dealing with a closed half. And from this, we can build certainly a nested. If we choose this point, we can simply nest it in an infinite collection of open balls. That's not a problem. And if we choose rational numbers for the top and the bottom, it'll be countable. So this is definitely a first countable space. So that's pretty good. Also, we can, using this, infinite unions of this can be constructed in a way where the lower limit, where the lower boundary of these open balls approaches any arbitrary number, real or rational, doesn't even matter. And because the infinite union of these things is acceptable, we can therefore create, actually, if we allow all of them to have the same upper boundary, right, the same upper limit A, but we start taking a series of B's that approach a point at the bottom, we can reproduce any open interval that way. So we can make any single open interval between, so if these B's are Bn and its limit is some limit L, we can produce any open interval LA on the line. So we can actually build any open set that was built in the Euclidean topology. But what's interesting is we can also build these half open sets too. So the lower limit topology is actually finer than the Euclidean topology, because not only can we reconstruct every open interval between any two numbers, we can also construct these half open intervals, which are open sets. So there are more open sets here than there are here, which is interesting. The problem, though, is despite that fact, despite the fact that the lower limit topology is finer than the Euclidean topology, it is not second countable. It's first countable, but not second countable. And the reason is if I take any countable basis, right, if I take any countable number of these, I can always, if this is one of them, say Bn, A, and this is another one, Bn plus 1, A, I can order them in a way where, say, Bn is lower than Bn plus 1, right? So the boundary of Bn is here and the boundary of Bn plus 1 is there. But if I take a point in between those two, and I just declare that to be the lower part of some interval, I can never use this countable basis to converge to that arbitrary point. So there are open sets, and since every interval, right, every interval, open interval, is an open set in the lower limit topology, I need to be able to build every interval from my basis. And I can, but if I restrict the basis now to be countable, then I can always find little open intervals between these countable elements of the basis that I can't construct. And therefore there are open sets that I cannot build out of the countable basis. So I cannot take any open set and build it out of a countable collection of these half-open intervals. Therefore, the lower limit topology is not second countable. It is first countable, but it's not second countable. The Euclidean topology, which is actually coarser than the lower limit topology, is first countable and second countable. So that's kind of interesting. Anyway, the point is that when we build manifolds, ultimately, they all have to be second countable, because that's a very important, it turns out that's a really nice property to keep our spaces from being really screwy. And they all have to be Hausdorff spaces, which is one of the better forms of separability. Okay, so now that we have that, we need to talk a little bit about continuity. So now let's have a look at the lower limit topology that we discussed very briefly in the last lecture, and we did really discuss it in terms of separability. The lower limit topology for a line segment looked like this. The basis sets were half open intervals. Those are the basis, they're all members of the topology, of the lower limit topology, and they form the basis. From this basis, you can construct any open interval, L and Lm, right? Where these are real numbers. L and M are members of the real numbers. And the reason we can do this is because you're allowed to take the infinite union of these of the basis to form all the open sets. So if I have a sequence, say Bn, and that sequence approaches L, right, then all I need is to take the infinite union over n of the sets Bn A like that, and what will end up happening is I'll have a bunch of closed ends that start limiting to L. And I'm allowed to take the infinite union of this, right? N goes to infinity, because infinite unions are okay when you're dealing with open sets. And so ultimately that infinite union is going to be L, A. So I pick A, and I create this sequence N, and I can create any open interval. So what's interesting about this lower limit topology is that every open interval is also a member of the topology. BA is where B and A are elements of the real numbers, right? B is an element of the real, and A is an element of the real. BA is an element of the topology of the lower limit. But all of these things here, that's the basis of the Euclidean topology. So what's interesting is that the basis of the Euclidean topology is actually all inside the lower limit topology. But the lower limit topology also has these guys. And these guys cannot be created in the Euclidean topology. In other words, there's no set of open sets in the Euclidean topology whose finite intersection or infinite union can produce this closed interval, right? Or this half-open interval. So in other words, the lower limit topology, or the Euclidean topology, is actually a subset of the lower limit topology, which is fascinating because this means that the lower limit topology, this thing is actually finer. I guess the word is finer often is used. And the Euclidean topology is coarser relative to one another. So that's just an interesting fact about this particular different type of topology. So it is an alternative topology on the line, but it's actually a finer topology. What's interesting about it, however, well, first of all, what about its countability? So let's take a look. Let's take a look at this point right here in the lower limits topology. Well, certainly I can create a nested, infinitely nested collection of open sets that surround the point. And if I restrict B and restrict A to the rational numbers, it's countable, right? So it's really, there's no trouble showing that it's first countable, right? It's clearly first countable. So the question is it second countable? Well, let's have a look at that. If it's second countable, then I should be able to find a basis that can create any open set. So let's say, and it's got to be a countable basis. So let's do this again. Let's say I have a sequence Bn and another sequence An. And n is an element of the integers, right? So I now have a countable basis. So let's assume there is a countable basis, right? And here it is. It's, well, actually, it should be am, where m is also an element of the integers. So whatever the basis is, I should be able to make any open set out of this countable basis. So, well, I'm going to organize the basis so that Bn plus 1 is less than Bn. So I'm going to sort of just organize them, and I'm going to put them here on the line where all of these, this is Bn, this is Bn plus 1, this is Bn plus 2, this is Bn plus 3, right? And if it's countable, I can do that, right? That's the whole point, it's countable. And you can immediately see the problem. You can see the problem because I can pick a point right here, and I know that that is I could choose that point to be the lower boundary of some open interval, which I know is an element of the topology, the lower limit topology. But how can I possibly create that open interval using this countable basis, right? I can't. So I need a countable basis that has a limit at that point. And if I rejigger the countable basis so that it has a limit at that point, I just do the same construction for some other point. And the fact is you can never create a countable basis that can create every open set at once. Therefore, the lower limit topology is not second countable. And that's really interesting because it's finer than the Euclidean topology, but the Euclidean topology is first countable and second countable. The point is these topological properties, when you really kind of dig into them, you've got to really keep track. They're not necessarily obviously hereditary in any clear way. Some of them are hereditary, and that meaning some imply others. There's always these weird circumstances where you think they might apply, but they don't. There's basically counterexamples galore. In fact, the very best book on topology is actually a book called Counterexamples in Topology, where all it does is explain all the counterexamples, and that's how you learn all of this stuff. Okay, so that was, so now we're done with countability, but our manifolds, we want our manifolds to be second countable, and we want our manifolds to be Hausdorff. And the reason is all manifolds are about things that are not dysfunctional, not weird, strange sets. And so when you see and you start studying general relativity and you deal with manifolds, we're always looking, you'll see that they mention, okay, we're going to assume that we've got something that's Hausdorff and second countable. And they kind of assume you know what that is. Well, now you do. And the reason is it's to keep you away from these weird possible spaces. And strange circumstance, because ultimately we're looking for coordinates, we're looking for things we can do calculus on, things where we can take derivatives, and you need these properties to be able to do those kinds of things. Also, continuity is really, really important in both, and both of these things loom large in continuity. In fact, that's our next subject. We're going to talk about continuity. All right, so now we're going to talk about continuity, and with topology, everything you thought you understood from your calculus courses and things like that gets suddenly mashed up and abstractified and becomes very kind of obtuse. But I think we've got enough tools now that it shouldn't be a big problem. The basic definition for continuity involves you have to, of course, have this idea of a function. So let me just remind you how this idea of a function works. We have a topological space. Now we have to talk about not just a function between a set x and y, but a topological space, right? So x has its own topology, and y has its own topology. And f is a function, just like any other, from one set to another, from the domain to the range. But the domain is endowed with a topology, and the range is endowed with a topology. And that's what allows us to define continuity. Otherwise, it's just a set. It's just a listing of a point here as corresponds to a point here corresponds to a point here. The notion of continuity wouldn't make any sense without a topology, without some concept of these open sets, which we now understand collect these points together in ways that are perhaps separable, perhaps not, with different degrees of separability. So ultimately, all this has to go and make contact with your epsilon delta sort of proof of limits. Remember the limit of a function x as x approaches a equals L. Remember, there was this whole notion of epsilon and delta to define this process. But you can do that because we have distance functions, and we know the distance between different points, and we have a lot of extra information that allows us to work with this. But when you don't have that extra information, you can still define continuity, but you have to use topology, and you have to have a well-understood topology of your two sets. So how does this work? Well, just remember that there's an inverse mapping, and I call it a mapping but not a function because it is possible that the inverse mapping is not a function. What makes a function is that for every spot in here, there is a unique spot over here. There's a unique value. For every element of x, there's a unique element of y. However, it could very well be that two elements of the domain go to the same element in the range, in which case the inverse function would not be unique, right? Going back in this direction, you would no longer have a function. So the inverse function doesn't have to be a function, but we're going to consider that the forward function is, and we'll call this the inverse mapping. By the way, the inverse function can be a function. If the original function is 1-to-1, then the inverse mapping will be at least a function, and we'll probably talk about that in a moment. So this is sort of the situation. Now our question is, how do we define continuity? And I'm just going to lay down the definition first, right? So going back to this circumstance, here's our point x, and this point we're going to call f of x, right, which is in the range of the function, right? And this is still this topological space, and this is y, so this one's x and this one's y. So now we ask the question, well, a function is continuous if any open set in y, right, any open set in y, if the preimage under the inverse is an open set in x, then you have a continuous, then f is continuous. So f is continuous if the preimage of, so if u is an element of the topology of y, any element of the topology of y, and then f, the inverse mapping of any u, that has to be an element of the topology of x. And that's how you define a continuous function f. That's how f is continuous. So the continuity of f depends critically on how the inverse mapping works on these open sets. Right? Now, the equivalent way of describing this in terms of neighborhoods, there's always this neighborhood version of things. In terms of neighborhoods, that's where you can really sense this epsilon delta nature of things. If I have a point and I have a neighborhood, an open neighborhood of the point in y and x, then the question is can I, so this is f of x here, and this is x here, I need to be able to find an open neighborhood here, where u is an element of the topology of x, and this is an open neighborhood here where v is an element of the topology of y. I need to be able to find an open neighborhood such that the image of u is a subset of v. So for every v that is an open neighborhood of f of x, for every open neighborhood, for the function to be continuous, I need to be able to find a open neighborhood in x where that entire open neighborhood maps to a subset of the open neighborhood over here. And that's where you get a sense of the epsilon delta. For some, you can also think of this in terms of measurement error. If an open neighborhood represents the error in a measurement of x, where the function is the measurement, right? This function might be considered a measurement. So you've got x, the measurement of x is f of x. Well, if you have an open neighborhood surrounding f of x, and you say, well, that's sort of the error in our measurement. Well, the question is can you find a neighborhood of x that's so tight that you can get so close to x that you can get inside that measurement error a neighborhood of the set y? This definition here is a definition of continuity of f. There's also a version of it that goes the other way, but the point is that this is entirely equivalent to this, it turns out. It turns out that for that neighborhood definition to be true, the pre-images of all the open sets in y have to be open sets in x. Okay, so now let's run some examples using the metric spaces we've been dealing with so far. Let's start with the Euclidean line, right? When I say the Euclidean line, I'm now talking about a line and its topology. So then I'm also going to use the nested interval line, and I'm also going to use the, what I've been calling the closed interval line. So I should actually take these points here, right? And then I'm going to talk about the cofinite line, right? The cofinite line. The closed interval line I'm going to have to rejigger so it goes from 0 to 1. Everything here is going to go from 0 to 1. All right, 0 to 1. It's just a simple shift in logic that gets you the infinite line, or the closed interval line. And then the lower limit topology. The lower limit topology will also include that, the lower limit topology. So now we're going to look at a function that goes from here down. So it's going to start. The domain is going to be the Euclidean line, and these are going to be the ranges. And then we'll try to reverse it. So the function is going to go this way. The inverse function, or the inverse mapping, I should say, is going to go that way. And the function we're going to work with is going to be f of x equals x. So this point here in the Euclidean line will be mapped to this point, this point, this point, and this point in each of these different cases. So we're really dealing with 4 functions. 1, 2, 3, 4 functions. All right. Now, let's ask the question: is this function continuous? Right? And the answer has to do with, well, we have to investigate the inverse mapping of open sets from each of these to the Euclidean line. So we'll start with the nested interval line, right? The nested interval line, the open set, one open set is, we can actually look at we can look at every single open set on the nested interval line, because the first one, just goes from 0 to 1/2, and the second goes to 1/3, and 2/3, 3/4, 4/5, all the way forever and ever. And each of these is an open interval on the line segment. The inverse image, right? The inverse image is f inverse of a point x equals x, right? It's the same darn thing. So this interval here is going to map to this interval here. And that interval here in the Euclidean line, that interval is certainly an element of the topology of the Euclidean line. So, and that captures every single nested interval. That'll be true for every nested interval. Every one of these, every one of the open sets in the nested line will map to an open set in the Euclidean line. So f is continuous. F is continuous because we've concluded that the inverse of f maps open sets, every open set from the nested interval line to open sets on the Euclidean line. So yes, f is continuous from the nested line to the Euclidean line. Or f is continuous. F is a continuous function from the Euclidean line to the nested line. What about for the closed interval line? Well, we now still have to investigate f inverse. But in this case, we do have a problem because, well, the closed interval line, first of all, it has all of these intervals in the topology that contain the middle. In this case, it would contain the point 1/2. In our previous example, it contained the point 0. All of these open sets, right, under this inverse mapping, map to open sets up here that happen to contain 1/2, but they're all open in the Euclidean topology. Therefore, all of these open intervals map just fine to open intervals. The problem, of course, aren't those. The problem are these. The problem are the closed intervals, right? This is also open. This half-open interval, right, that includes this boundary, that's open here, but it's not open here, right? That mapping, under this mapping, you're going to get the closed interval on this side and the open, you're going to get a half-open interval up here. And what's worse is that the half part that's closed contains a point that's not even in the set. So that's out. So it is not a continuous mapping. F, this function, f of x equals x, going from Euclidean to the closed interval line, is not continuous because the inverse image does not map every open set to an open set. So what about the cofinite topology? Well, in order to exemplify that, we have to kind of pick a couple points to omit to generate an open set in the cofinite topology. So now we have an open set in the cofinite topology. It consists of these three open intervals. These three open intervals map to three open intervals under the inverse mapping of our function under investigation. So we have three open intervals in the Euclidean topology. Each one of those three is open in the Euclidean topology, but the union of any open sets is open. So this maps just fine to the same, let's see if I can draw it up here, to the same three intervals up here. So this maps just fine. That's an open point. And because of that, we now know that this function here, f of x equals x, that's continuous from the Euclidean line to the cofinite line without any trouble. The lower limit line, of course, you're going to have the same problem we had with the closed interval line. In the lower limit line, I have an open interval. This is open in the lower limit topology. This half-open interval is open in the lower limit. Under this inverse mapping, it's going to go up here to, it's going to go right there to the same closed interval. And this closed interval, this half-closed interval, is not an open set in the Euclidean topology. So this is not a continuous function under the lower limit topology. Now, if we have a look at this in reverse, things change quite a bit, right? If we swap all this out so that, let's swap it all out. actually I didn't read. So now we're dealing with four functions that go this way, and the inverse function goes from the Euclidean plane back. How does that work out? Well, now we've got a lot more problems, right? Because let's see what those problems are if we can figure them out. Imagine that we took. So now we have to ask, well, do the open sets of the Euclidean topology, how do they map to open sets for these various other topologies? And all I have to do to make mincemeat of this problem is pick just one lousy little open interval, right? And right away, you can see that that interval in the nested interval topology fails. That's not an open set. This is not an open set in the nested interval topology, right? Because it's actually tucked inside an open set. It's contained in an open set, but it's not an open set itself, so that doesn't work. In the closed interval topology, we get this thing. Well, that actually works, right? Because we know that the oh, I'm sorry, no, this doesn't work at all. My bad. This works in the lower limit, but it won't work in the closed interval topology because this open set, it's on the entirely, it doesn't contain a half, right? It's got to contain this midpoint. Remember, all the open sets in the closed interval topology were either open intervals that contain the midpoint or these half open intervals, and that's neither one. So that's out. So F from the closed interval topology to the Euclidean topology is not continuous because the inverse of open sets in the Euclidean topology do not land as open sets in the closed interval topology. How about the cofinite topology? Well, that's not good either, right? Because in the cofinite topology, if I take this green set down here, then remember this is just this interval here in the cofinite topology it's never going to be an open set because the cofinite topology its open sets only emit a finite number of points, right? So in order to get this interval, I'd have to emit all of these points and all of those points, and you can't do that. So the inverse image, the inverse mapping of our function from the Euclidean space to the cofinite topology, the Euclidean line to the cofinite line, that's not continuous either. And then the last one to look at is the the lower limit topology. Lower limit topology we're good because we've already shown that any open interval in the lower limit topology can be created using this basis of half open intervals, B and A, and it involved creating a limit Bn that approaches whatever this point is on the lower limit of this open interval. So this is good, and of course it should be. We're hoping it's good because remember the lower limit topology was finer than the Euclidean topology was, and so we're hoping that the continuity issues would be less of a problem. In fact, speaking of being fine, let's throw one more line in here. Let's throw one more type of line. Let's throw in the line with the open interval with the discrete topology. Remember, the discrete topology says that every point is an open set. So now if we drop this down here, of course that open interval is an open set in the discrete topology without any trouble because any subset in the discrete topology is open. And likewise, if it went the other way, right, if we went back to our original function where we were mapping from here to here with F, the discrete topology, we have a huge problem, right, because a closed interval is a subset of the discrete topology, and a closed interval is open in the discrete topology, but a closed interval is not open in the Euclidean line. Therefore, functions from the Euclidean line to the discrete line have a lot of continuity problems. And in fact, they're not continuous. No function would be continuous, I don't think, in that circumstance. Okay, so I think we belabored this idea quite a bit. It's just a little counterintuitive because the definition of continuity, you have to check the inverse mapping of the different topologies. Now, the point is in manifolds, when you're dealing with manifolds, we're going to be dealing with continuous functions from one manifold to another. And it's definitely defined this way, but the point is the topology of the manifolds we're dealing with are not these weird topologies, right? They're much more like the Euclidean topology. They're robust to capture everything we need. The notions of continuity are good. You're not dealing with mapping from one weird topology to another. And that's an important thing. So when you start studying manifolds carefully, you'll start saying, well, let's assume we have a topological space that's Hausdorff, second countable, and a continuous function. You don't have to go in there and double and triple check this because you're dealing with manifolds that do not have unusual topologies. In fact, one thing that we are interested in is functions that are very, very powerful, called homeomorphisms. And let me talk about that for a moment. So the homeomorphic functions look a little, we've talked about functions from one topological space to another. It could be that the inverse image is also a function. And that would basically mean that to check the continuity of the inverse image, you would have to use the function itself, right? Because the inverse of the inverse function in that circumstance would be the function itself. So if this is a function and this is a function, and it's continuous in both directions, which means that the whole exercise we did for that use this function to check the continuity of this function, if we did that whole exercise again and use this function to check the continuity of that function, and let's say it's all true, everything's continuous. This is a continuous function, and this is a continuous function. That means this is a completely continuous mapping from this topological space to this topological space. And its inverse mapping is also completely continuous. If that's the case, then what you're dealing with is something called a homeomorphism. And a homeomorphism is a very important kind of function because there are lots of topological properties that are actually important that homeomorphisms preserve. So this space will have a certain kind of set of topological properties, and this space will. For example, separability. The separability property of this space, and there'll be a separability property for this space. And the homeomorphism is something, so that's a kind of a property. There's another property called compactness. In fact, maybe I could just write them down. There's compactness, there's separability, there's connectedness, right? And there's a few others, right? And the question is if I have a homeomorphism, does it preserve the compactness properties? Does it preserve the separability properties? Does it preserve the connectedness properties? Meaning if this is compact in a certain way, is this compact in the same way? Is this separable in a certain way? Is this separable in the same way? If this is connected, is this one connected under a homeomorphism? Just for reference, these properties are in fact preserved under homeomorphisms. Okay, so now ultimately this is all going to help us understand how manifolds are constructed. It's a little bit more than we need to know because manifolds are inevitably Hausdorff and second countable, so knowing all of the other ones isn't so important, but it gives you a little more confidence in dealing with the proofs that you might see in other textbooks out there. So our next lecture will actually start to talk about manifolds.